In this lecture, we are going to study how to generate IR from the CAST. In other words, we are going to study how to implement the IRgen pass inside the compiler. So this is about homework 2, which is to implement the IRgen, which is annotated as an homework 2 in the skeleton code. So please go to the repository and search for the homework 2, and there will be the places where you're going to implement your logic, IRgen logic. So this homework will be evaluated as follows. So you're going to generate an IR from a C, all right? So we're going to check if an execution result of C program is equal to the generated IR's execution result. So if it satisfies for randomly generated files, then it is going to be okay. So here is a few scripts to test whether this criteria is actually met or not. So you first implement your IRgen and then do cargo test example IRgen. Then it is going to check whether the criteria here, execution results, are the same for C and IR. It is checked for some set of examples that is already in the repository. And also, there should be it should be provided the fudger. The fudger will randomly generate the test inputs and see if this criteria holds for the randomly generated C programs. So if these two criteria are met, then you're going to be okay. Your submission will be marked as okay. So I'm going to announce how to submit the homework in a later slide or the GitHub repository. And in this video, we are going to study how to actually implement this IRgen. So that, I mean, in other words, how to do this homework. So recall from the introduction sections that IRgen is translating a CST AST into IR-AST. You all know about C, right? So I'm going to discuss IR a little bit. In the previous lecture, we discussed that IR is a control flow graph-based language where registers play a key role in calculating the results. And in contrast to C, it doesn't have ambiguous names. So every names are resolved so that the IR has only unambiguous references to the variables and registers. Also, every expressions and variables and registers are explicitly annotated with types. So there's no need to infer the type of a component of an IR. And also, we are going to discuss this static single assignment aspect of the IR in a later slide. So in IRgen, you're going to implement the translation from CST-AST to IR-AST. And in particular, you're going to translate what is called C translation units. So you can think of it as a file, just a single C file after all the compiler directives are resolved. For example, shop include and shop defines are all resolved in these translation units. And you're going to translate such a preprocessed C program into an IR. So we're going to study such as subtopics. So how to translate variable declarations. How to translate, for example, int x equals 42. How to translate the function definition. For example, how to translate the main function. And inside the function, we should translate expressions, complex statements, and control flows like if then else statements and the while, do while, switch cases, and blah blah. And we also need to translate variables. For example, the variable x in the C should be translated into the IR using registers and local variables and global variables. We need to deal with such a translation of variables. And furthermore, we call that IR has unambiguous names while C has ambiguous names. The name X, for example, can refer to multiple allocations inside C. And we need to disambiguate this naming. And we are going to study how to resolve such names. And furthermore, we are going to study how to translate complex types, such as arrays or structs. And this is basically the content of the IRgen. So it is going to be a series of lectures instead of a single lecture that explains how to implement this IRgen. So this is the first video, and we are going to study first a few basic concepts and how to translate the basic structures inside the C translation unit. Probably for the more advanced topics like name resolution or arraying structs, we are going to deal with this in a later video. So first things first, how to translate a C translation unit or a C source file. So C source file or translation unit consists of multiple declarations. So for example, here, this is an example, a C file, and it consists of 3 declarations. The first thing is this integer variable declaration, and the second thing is this function definition of a function named foo, and this is the main function definition. So these 3 are each of them is a declaration, and a translation unit is consisting of multiple declarations. Unfortunately, in C, we need to translate each declaration one by one. So, for example, in this program, the translation of this main function doesn't affect the translation of this foo function. So we can translate each of them one by one. So there is no interferences among multiple declarations, except that the names are resolved. Names should be resolved in the name resolution. We should consider the order of the declarations. For example, when the program is like this x and this x should refer to the global variable this. But if this is defined here, which is defined after this foo function, then this x is no longer resolved to this global declaration. So except for such name resolution differences that are depending on the order of the declarations, the declaration, the translation of each declaration is largely independent with each other. And then we are going to study how to translate each declaration. A declaration is either variable declaration or function definition. So for variable declaration, it is very straightforward. We just translate types, which is written in CAIST, into IR's type, which is very similarly defined to the AST types, CAIST types. And fortunately, these IR types are already provided in the skeleton code, so you don't need to define your own IR types. So you can just reuse the existing skeleton code's IR types. And furthermore, we need to deal with a translation of single line but multiple variable declarations like this. If you declare x and y at the same time, then you are going to declare 2 variables at the same time in a single line. You need to deal with such a cases. So in IR, we are going to declare 1 variable at a time, but in C, you can declare multiple variables at the same time. So we need to split them into multiple declarations. Furthermore, we need to translate initializer to values. For example, in this code, this is declaring a variable x that is array size 2 of integers, and it is initialized with these values 42 and 37. And we need to interpret this initializer into the value that should be assigned to the variable initially. Okay, and on the other hand, we need to also deal with the function definitions. We need to translate C function definitions into IR function definitions. And usually that is where the interesting things happen. I mean, they have a lot of control structures, a lot of expressions, and blah blah. And that is the most complex part of the translation, actually. So in this IRgen, in the KCC's IRgen's design, we aim to develop a simple and correct function definition translation instead of very efficient and optimized IR generation. So the reason here is that we need to focus on simplicity and correctness because IRgen is already difficult to implement because we need to take care of all the corner cases of C. We don't want to mix the difficulty of corner cases of C into and the difficulty of achieving efficiency and optimizations. So all optimizations and efficiency will later be dealt with in optimization passes like mem2res, GVN, dead code, etc., etc. Actually, this design is inspired by other mainstream compilers as well. So GCC and LLVM, which are the mainstream C compilers, are also designed in this way. IRgen is simple and it should be correct, and all the efficiency criteria is taken care of by optimization passes. So they generate a very stupid IR, which is very inefficient, but that's okay because as far as it is correct, the efficiency will be taken care of by the later optimization passes. So now let me explain how to explain the function definitions in a simple and correct way. So let me start with an expression. So function, a C function is consisting of various constructs like expressions and statements and various control flow related statements, etc., etc. But we first need to explain how to translate a very basic objects, the most basic objects in the C function, which is expression. For example, we want to translate an expression like this: x equals a plus b. This is a simple assignment after the calculation of this addition. So this is translated into IR like this. Instead of directly working on the memory value, this a is a variable, and let's say that this a is stored in a local variable, then it is going to be a memory location because every local variable is actually a memory. The address of them can be taken, so that's the reason why they are memory locations. So in IR, we first load from the memory location here, A. And we are going to assign this into a register, TA. Let's say that this T stands for temporary. So this is a temporary register that is representing the value of A at this time. And similarly, we should load the value the value B from the memory location B, and we store the value into this register, TB. There are two temporary registers that contains A and B respectively. So the reason why we don't directly add the values in the memory values is that the IR only allows the arithmetic operations for the registers. They don't allow arithmetic operations on the memory values. That's the reason why we first load the memory values into register values and then perform the addition. We perform this addition and then store this result of this addition into a temporary register that is containing the value of x, and then store this value into the memory location x. Okay, so as you can see that this is very verbose. One line of code is translated into 4 lines of code, but that's for simplicity. We can say that every line of this generated IR is simple, only doing one thing at a time. It is loading the value from the memory. It is loading value from the memory. It is adding the values inside the registers, and it is storing the value to the memory. So, but however, here in C program, it is performing various things at the same time. Loading, adding, and storing at the same time. So we are basically decomposing multiple actions inside this expression into a multi-line, multi-instruction program. So that each code inside it is doing only one thing at a time. So this form of the code is usually called as a 3-address form because there are at most 3 addresses inside these instructions. It is going to contain 1, 2, 3. That is the operands of the instructions, 2 operands of the instructions, and 1 target instruction, target register. And here we only have 2 addresses: the memory value of the loaded pointer here, and the target register here. And similarly, we only have 2 addresses here. So that's the reason why we can achieve the simplicity from this a little bit verbose IR, which is generated from the KAIST. Furthermore, we can translate complex expressions into this kind of IR like this. If we have a little bit more complex expressions, x equals a plus b and then plus c, then we can translate like this. We first load a like this. This is exactly the same with this code here. Load a and load b, and then calculate the summation of a and b here. So now we don't need to store the intermediate value to the memory because this is not a memory value. This is not an address. We cannot take the address of this intermediate results, so it can just reside in the register. So and TAB is such a register that is containing the intermediate value, intermediate summation of a and b. And then we are going to load C, which is going to be used in the second addition here, and then calculate Tx, which is the summation of a plus b, which is stored in the register TAB, and the value of C, which is stored in the register TC. And then the result Tx is stored in the memory location X here. That has the exactly same meaning as the original C program. Load A and B, then add the values, and then load C, and add the value, and store the final calculation into the memory location here. So as I said, this form of the code is usually called as 3-address forms or 3-address codes, where each instruction has at most 3 addresses. And you can see that every complex expression can actually be translated into 3-address codes. So if there are more arithmetic operations like multiplication, division, and other things in a complex way, we can recursively translate this program, this very complex expression, into such a form using 3-address codes. It is still very verbose. It is translating a very short code into multiple lines of instructions, but as I said, it is simple. Every instruction is doing only one thing at a time. So that's the purpose of the IRgen: simplicity and correctness. Now let's turn to statement. You can think of expression as something that is producing a value, but on the other end, the C statement is an instruction doing something. Instead of producing a value, it is imperatively demanding the machine to perform some operations. For example, a while statement, an assignment statement, an if-then-else statement are saying that, oh, the machine should do some operation. On the other end, expressions are calculating values. So this is the difference between C expressions and C statements. And the statements are a recursive data structure. For example, in this while statement, it is consisting of an expression that is meant to be a condition for the while loop, and the inner statement that is executed repeatedly until the condition is no longer met. So it is a very recursive structure because this A in turn can contain other while statements and if then else statements and other things as well. So it can have a very nested level of statements tree. So in order to translate such a recursively defined statement, we need to do it compositionally because otherwise it is too difficult for humankind. So we need to translate, for example, this composite statement A and then B into the IR by roughly translating A first and then translating B later. Similarly, when we are translating this Y statement, we need to first translate the expression here, condition here, and then translate the inner statement A here, and then add some logic, some extra logic for dealing with the recursive, the loop later of this Y statement. So otherwise, it is too difficult to translate this Y statement in one way. So we need to basically compose the translation result of C and A, and then do some extra logic to deal with the Y statement. So here is a simple example, which is roughly corresponding to A semicolon B. This is the two statements, x equals A and B and y equals x plus C. And these two are forming a complex statement that is consisting of two sub-statements, two assignment statements. And translation is easy. We first translate the first statement. We first load A, load B, and calculate the addition and store the value. Just the juxtaposition of statements is easy to translate because we can just translate the first statement and then translate the second statement in right after the result of translation result of the first statement. So it is very easy. Just the concatenation is enough for translating this A semicolon B. But Y statement is going to be a little bit difficult because we need to somehow deal with the logic here, the logic of the while loop here. If C is true, then we are going to do A, and then try again from the beginning of this while loop. On the other end, if C is false, then we just break out and go to the next statement. So that kind of extra logic should be dealt with in the translation. So we are going to deal with such an extra logic in a later slide. Again, this is inefficient because we are storing the value of x here and then loading again, which is not strictly necessary because the value stored in x here and the value loaded from x here should be the same. But we translate in IRgen, we translate this in this way because even though it is inefficient, because it is much simpler, we can just translate the first statement and the second statement without considering the relationship between the two statements. We translate each of them. So that's much simpler and it's much less error prone. Now let's discuss how to translate control flows like a Y statement as we just saw before, and if then else or other kind of control flow changing statement in C. So for example, here, when we're translating if C then A else B, we are going to do this. We first translate the C here. There can be a bunch of instructions that calculates the value of C here. And depending on the value of the C, you jump to A if it is true, or you jump to B if the conditional value is evaluated to 0. So in A, you are going to do what the statement A is going to say, to whatever logic that is described in this statement A. And here, it is also translating the logic that is described in here, the block B here. And after this if then else statement, you are going to jump to the continuation block. So after this if then else statement, you are going to jump to somewhere from which you execute the remaining executions. So if there is a code that is executed after this if then else, then it is going to be translated into this continuation block. And you may see that there is a recursive structure. A can also be a very control flow rich statement. It can have if then else, it can have while loop, blah, blah, blah. So we need to do it basically recursively. So in other words, we need to translate it in a syntax-directed fashion or AEST walking fashion. So it should be done compositionally. So in the translation of this statement, we are going to deal with the translation of C, A, and B. And in turn, in the translation of A, we need to deal with the sub-statement of the statement A here. So it should be done recursively. That's the meaning of the compositional translation or the syntax-directed translation or AEST walking translation. And now the question is, what is the interface for the recursion? So when you're translating this if then else, then we are going to recurse into the translation of this A, and we need to pass some information that is necessary for the translation of A into an IR. So then what is such an information? What is the interface between the caller and the callee of the recursion? So that is the question I'd like to answer in this slide. And here is the high-level structure of the recursion that I'm going to use for the translation of if then else. And in the course of explaining this recursive translation of this if then else, the interface between the caller and callee will be made explicit. So it is going to be what is called a translation unit. The interface is going to be called translation context that is consisting of the committed blocks that you already finished translating. There can be a very rich control structure graph here. Jump to here, 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 here. And it is also consisting of the current block that is currently being constructed. So this is the current block that you are going to onto which you're going to translate the given statement. And you're going to have the block's ID and also the existing instructions that was previously translated so far. So now, if you're given this context, the committed blocks and the current block that is being constructed, then now assume that you are going to translate if C, then A, and else B. The first thing to do is translate the C here, because it is the first thing to execute in this conditional statement. You translate C here from the original block, but you have to be notified that C may also be consisting of some control flows. So maybe the block can be changed, but anyway, you translate C from the current block. And at the end of the translation of this C, you're going to get the value that is representing the translation result of this expression C. And now you're going to create blocks and block IDs for the branches, then and else branches, because you're going to jump to the next block depending on the value of C. And in the next blocks, you're going to execute either A or B. And you need to translate this A and B into the new blocks. So that's the reason why you need to create new blocks with new block IDs. And third, and now you're going to commit the current block. Here, the current block is finished its translation. After translation of the C, there will be no longer instructions that will be executed in this block because it is already it is going to jump to the next block, and which is depending on the value of this C. And if it is true, and it is going to jump to this block. And if the value of C is false, then it is going to jump to this block. So that's the end of the job of this current block. So jumping to the next block. And in the next block, A or B will be executed. So that's the job of the later translation. So that's the reason why the job of this block is done. So we finish we are just mark it as committed. There will be no longer changes to the current block. Now, after doing this, we are going to create the block for the continuation. So after executing this if then else statement, you're going to jump back to somewhere, and that somewhere is this next block or the continuation block that is just created with. The reason why these blocks are dotted here is that these blocks are not yet committed. It is not yet finished translation. We need to do it in a later stage of the translation. So that's the reason why we mark it as tentative and not yet committed. So after this, we are going to translate A. So A is executed only if the condition C is evaluated true, right? And if it is true, we are going to go to this left block. So that's the reason why we translate A from the left block or the then block we just created. So A is translated here. So maybe it is possible that the block can be changed because A can also have its own control flows. So maybe the block can be changed. But that's not but that's okay because the translation context will be preserved. So at the end of the translation of this A, the current context translation context will be the block that is not yet committed, that is still tentative, but that is containing the last instructions of the block A. So that's the reason why. So this block will be containing the last instruction of A, and that's the reason why we need to jump back to the continuation block here. So we finished translation of this A. So we commit the current block here onto which the statement A was translated, and we commit this block with a jump to the continuation block here. So to summarize this translation, we first create the blocks here, and we jump to this block if the C is true, and then we translate A, and at the end of the translation of this A, we jump back to the continuation block here, and finish the translation of this A here by marking this block as committed. The same thing happened for the then branch, else branch. We translate B from the newly created block ID for the else branch, and then commit with jumping to the continuation block here. And as I said, this can be a recursive computation because during the during the translation of A, inside the translation of A, there can be more control flows, and it can be dealt with in a recursive call that translates the statement A. And here, maybe there can be another if then else statement, and then there can be other blocks that is created due to this kind of translation. But at the end of the translation, it is going back to the continuation block. So that is the reason why that's the reason why this translation context plays a key role in this translation, and it can be done in a recursive fashion. Now, after translating this if C then A else B statement, we are going to continue the translation using this continuation block as the current block. It is the new current block. So from after this statement, if there is another statement, for example x here, then it is going to be translated into after this current block. So that's basically the design here. So in this way, we can translate control flows in the C statements into control graphs. Control flow graphs. Now let's think of this translation. So maybe it is possible that this kind of procedure may create too many blocks that is not actually necessary. But that's okay, because the focus of this IRgen is not efficiency, but simplicity and correctness. By systematically translating this statement recursively, we can implement a simple and correct IRgen, even if it is very inefficient. But that's okay. So similar to if-then else statements, we can translate other control flow statements as well. For example, loops, while, do, break, continue. And furthermore, we can translate these conditional expressions in a similar fashion. So this A question mark B colon C is very similar to if-then else statement. So it is computing A, and depending on the value of the A, it is calculate B or C. And what's different from the if-then else statement is that it is actually returning a value, the B or C here. Except for that, it is almost the same with this if-then else statement. So we need to do a similar translation we did for the if-then else statement here, creating new blocks here, and translating the then value here, and translating else value here, and then jump to the continuation block and use the value of A or B in the continuation block. So that is necessary for translation of these conditional expressions. And translations for for loops or while loops or do while loops are very similar. You need to create new blocks basically. Instead of creating blocks for then branches and else branches, you need to create, for example, initializers, blocks for initializers in for, body, and increment, and condition. You also have to create a block for continuation that is meant to be the block that will be executed after this for loop. On the other end, a while loop should create new blocks for conditions and the body and the continuation, and similarly for do while as well. And also switch statements should deal with control flows, right? So it should create a few blocks that is going to be compare the given value of the switch statement, and depending on the value, it jumps to the cases. And each case should have new blocks here. And and it also requires the continuation block that will be executed after the switch statement. Furthermore, in order to support a break and continue inside this for while do while statement, we need to remember some block IDs. For example, inside for, when a break is met, you need to go directly to the continuation block. On the other end, if you are going to make a continue statement, then you need to go directly to the increment block here. So that's the reason why we have to remember uh, some block IDs in the if for the translation of for while, do while, and their break and continue statements. So let me look at some examples here. Okay. Okay. Sure. Okay. If you have a for statement, that's right here. And say in the current translation, it is there's a current block. And if you meet this for statement, then you have to create new blocks for the initializer and the condition and increment. So the first block, let's say this is the current block. And you need to jump to the initializer block. And after initialization of after the initialization, you need to jump to the condition block. That is checking if I is less than 10 or not. And depending on the condition here, it is going to jump to either the body block or if it is not met, it is going to jump to the continuation block. And after the body is finished being executed, it is going to jump to the increment block that is going to increment the value of I here. And increment block is going to jump to the after increment, you are going to jump to the condition block that is already created here. So here's the execution plan. In the current block, you first go to the initializer block, and then after initializing the values, you're going to go to the check the condition. And depending on the value of this, you're going to either go to the body block or the continuation block. And if the body is not after this body block, you're going to go to the increment block. And after this increment block, you're going to go back to the conditional block here. So you need to create 5 blocks here. And that is corresponding to this 5 blocks. So similarly, for while statement, you need to create a condition, body, continuation blocks. And for do while statement, you need to create a body, condition, continuation blocks. For an additional topic, you may think how to translate C++ exceptions, which is actually not the scope of this course. But exceptions introduce a very complex control flows, so you may need to take care of those control flows in the IR generation very specially. So you may think about how to translate C++ exceptions, and if you're curious about, you can see how the mainstream compilers such as GCC and Clang would translate this. The next topic about IRgen is translating variables, and in particular, translating global and local variables. So, for example, in this statement, the %ti equals load a, we are going to load the value of a pointer a. where this a variable a should be translated into some register in IR. So all the target of the load should be a pointer, and a is not a valid construct in IR, and it should be represented as a register or other kinds of storage locations in the IR. And there are two kinds of locations in IR, which is the global variable, which begins with this the a circle. What do you call it? It is the separator for an email address at. So this at g is a global variable, and at g colon int means that g is a pointer to integer, and the block pointed to by this g, it contains the value of the value g. So it is important to note that this at g is its type is a pointer to integer. So this int g is translated into at g colon int. This is going to be a pointer that is pointing to the value that is meant to store the same value as in C. This foo is also a global variable. A foo is a global variable that is containing a function pointer to the function that is being translated here. On the other hand, the other class of variables are registers, which begins with this ampersand. For example, this ampersand L colon integer means that you're going to declare a local variable of type integer, and this %L is going to store a pointer to the local variable and local allocation. So the type of this %L is the pointer to integer instead of just integer. The reason why it is the at g and this %L type is pointer to integer is that you can take an address of those variables. Because you can take an address, it should have a pointer value. It should have an address, and this at g and %L is going to store the address, and this address will later be used to load the value stored in those variables. For example, if you're going to return g plus l, so the meaning of this is that you first load the value that is stored in g, and then you load the value stored in L, like this. Tg is the value loaded from the pointer that is stored written in this atg, and %L is loading the value from the pointer that is stored in this %L. These two are containing pointers, and these pointer values are loaded into this TG and TL registers. And later you're going to calculate the summation of these two and then return this. So in this way, you can express global and local variables and translate the global and local variables in C into IR while you can allow the programmer to take address of those. So for example, if you take the address of G, %G, then it is simply translated into this at G because it is the pointer value you want. So here is a kind of recall of what I just described. %G is a global variable declaration and add its meaning for the global variable. And %L is a local variable declaration, and in particular, for local allocations, all local variable declarations should be declared at the beginning of a function. So in C, you can declare a variable inside the other construct, the nested structure. For example, inside a block or inside a for loop. But in IR, you can only declare a local variable only at the top of the function, only at the beginning of the function. So it makes the job of the memory allocator much more simpler. So it is going to be declared at the beginning of the function, like you're going to declare %L, which is of type int, so that %L's type should be pointer to integer. And this allocation is allocated here. Okay, now we have translated variables, and the remaining question is how to resolve names, how to disambiguate the same names that the references to different locations or different variables. So here's an example. V is declared 3 times. At the beginning, it's declared as a global variable here at the beginning, and later it is declared as a local variable at the beginning of the function foo, and later it is again declared as a local variable that is defined within this block that is consisting of 2 statements. And at the beginning, the global variable v is visible to everywhere, and you can think of it as a layered 0 variable. So now all the variables will have its own layers. So it is layer 0, and because of this block here, it is the function is starting a block. It becomes layer 1, and this v equals 2 is declared as a layer 1 variable. And because of this another block here, beginning of the block here, the variable v equals 3 is in the new layer, that is layer 2. So it has a nested structure. So layer 0 and layer 1 has a nested block, and inside the nested block has the nested block has layer 2, etc., etc. And this v is the reference twice as in assertions, and in first assertion it should point to v equals 3 variable because it is the most recent declaration of the variable. So this assertion is inside layer 2 here. So this v should be resolved into the variable that is declared in layer 2, which is v equals 3. On the other hand, in the later assertion, v equals 2, so this should be resolved into the second declaration, which is v equals 2, because the v equals 3 declaration is exited with the block. So as soon as the block is exited, the v is no longer meaning the variable declaration v equals 3, and it is going to declare it is going to mean v equals 2 here, declared in the third line. And after this last bracket, the layer 1 has also ended. So v now means the global variable v after the last line of the code. So in order to express this idea, the nested structure of the declaration and the layered translation of the variables, we manipulate as what is called a symbol table. This is basically a layers or a list of mapping from name to value, and each layer's mapping is meaning the variable v that is referenced in the code should resolve to some value or some variable, some register that is holding the pointer to the local allocations or global allocations. So here layer 0 or level 0 is for global variables. So that's the meaning of this layer 0. It has a global, it is declared as a global variable. So layer 0, it is put into layer 0. And higher level or higher layer contains the local variables. And when you're going to start a block with the bracket, then it is going to create another level, another higher level. So afterwards, all the declarations and references are done in this way, in this level. So as soon as the block is terminated, then the layer is popped up, so that all the old declarations that was inside the block is now gone. So the symbol tables are manipulated. So in summary, symbol tables are manipulated as follows. When you are going to meet the bracket, starting bracket, then you're going to push a new layer on top of your symbol table. And when you meet the ending bracket, then you are going to pop the top layer, so that all the mappings that was recorded in the top layer is gone with the block. And if you're going to declare a variable, then you're going to add the mapping. For example, v should point to some variable, should point to some location, let's say ampersand v1, to the top layer. And if you're going to reference the variable like v here, then you're going to consult the most, the highest layer or highest levels mapping, and see what's going to be the meaning of the variable v here. So here's a little bit abstract explanation, and let's look at some example here. So let's say that the code is like this. The global variable v is declared, and you're going to translate the function foo here. And at the time that this function is translated, you already know that there are two global variables, v and foo. And v's type is integer, and foo's type is a function returning integer. So as I explained, v's type, this at v's type should be pointer to integer rather than integer, because this should be the pointer instead of the value. Okay, now let's translate this function one by one, resolving the names. So at the beginning of the function, you don't know what kind of local variables are declared in the function. So the local variables are empty at the beginning. Now, at the layer 0, you are going to have a mapping like this. V points to the at v, because the name v should be resolved into the global variable v, and foo should be resolved to the global variable declaration foo. That is a function pointer. And at the beginning of the function, it is going to push a new layer at the top, the layer 1, because it is beginning a block here. So far so good. Now we are going to translate the declaration. So as soon as you make the declaration, you have to add the declaration to your list of local variables. So you're going to add ampersand v2. So this 2 is the suffix 2 is appended in order to disambiguate names. So actually this name is not semantically meaningful. So we are going to add a local variable, whatever it is called, but we are going to call it ampersand v2, which is going to store a pointer to the variable that is just declared in this integer v equals 2. And at the same time, you have to update your symbol table. So you have to update the top layers mapping by adding the mapping from v to the just declared variable ampersand v2. That means that as far as you're at the top level layer, as far as you're not, as far as the top block has not yet exited, the variable v should mean ampersand v2, and the v should resolve to ampersand v2. So far so good. And you are going to enter into another scope by entering a block, and as a result, you are going to create another layer, which is layer 2. And at the beginning of this layer, it has no mapping. That means there's no declarations that was defined so far. Now, when you made another declaration, integer v equals 3, then you made another local variable. So you add it to your list of local variables. So let's say this is ampersand v3. Again, the name is not semantically meaningful, but we're just going to use v3 in order to disambiguate the local variables. So these two local declarations of v are different, and that's the reason why we have two local variable pointers, ampersand v2 and ampersand v3. And at the same time, the symbol table is updated. The top level layer 2, now has a mapping from v to ampersand v3. That means until this block is exited, v should mean ampersand v3. That is just declared in this block. Now we are going to interpret assertion here, and we are looking up a variable v, right? And in order to do that, we first need to resolve this v in the symbol table. And fortunately, at the top level, we have a v, and v is pointing to ampersand v3. And now you can see that, oh, v should point to ampersand v3, and in order to compare the value of v with 3, we have to first load from ampersand v3. That's the reason why this assertion is first translated into load of v3 and compare the loaded value with 3, and then assert that this comparison is true. So in summary of this line, the most important fact is that the top layer has a mapping from v to ampersand v3, and that's the reason why the variable v here should resolve to ampersand v3. Now, this code block is exited, and as a result, the last layer should be popped up. That means the last layer that was containing the mapping from v to ampersand v3 is just finished, and v no longer points to ampersand v3 from now on. The reason is that the block in which this v is declared is exited, and it is no longer referenceable. Now we are going to read v again, but at this time the symbol table's top layer is level 1, and it contains the mapping from v to ampersand v2, and that's the reason why this load ampersand the comparison of this v and 2 is translated into these three lines. First, you load from ampersand v2, which was mapped by v at the top layer of the symbol table, and then you can compare the loaded value with 2, and then you assert that the comparison should be true. Now, after this function's ending bracket, the top layer is popped up, so you now have only one layer, which is the layer 0 for global variables. So in this way, you can disambiguate the multiple local variable and global variable declarations by using symbol tables. And in this example, we only discussed a very simple control flow. But in the presence of if then else or other control flow statements, we need to take care of the symbol tables and control flows at the same time. And this is the high level idea for how to do that. So in this if then else statement, if C, then in bracket you do A, or else in another bracket you do B. The main difference from the previous example is that A should have its own scope and B should have its own scope too. And as a result, we need to add the layer for the translation A before starting the translation of A, and we also need to pop the top layer at the end of the translation of A. Similar to B. At the beginning of the translation of B, you have to insert a layer to the symbol table. And at the end of the translation of B, you have to pop the thumb layer of the symbol table. So how to do this? So recall that if then else is translated like this. You first translate C and you create two blocks for then and else branches, and then you finish and commit the current block, and you create another block that is meant to be the continuation, and you translate A. But before translating A, you first enter the scope and create a new layer in the symbol table, and then translate A in the then block, and then exit the scope. Or in other words, you pop the thumb layer in the symbol table. And you finish the block by jumping to the continuation block. And similarly, before translating B, you first enter the scope, inserting a new layer at the top of the symbol table, and you translate B. And at the end of the translation of B, you pop the thumb layer from the symbol table and finish the block here. So in this way, you can make sure that A and B has its own scope, and all the declarations that was declared in A and B are forgotten at the end of the block. So that's the purpose of this enter scope and exit scope, or in other words, that's the purpose of creating and deleting a layer inside the symbol table. So before moving on to the next topic, I'd like to stop here. And in the next lecture, we are going to look at the code of the IRgen, the model solution to the IRgen, and how these ideas is implemented in the compiler code. So, and after looking at the code, in the next to the next lecture, we are going to look at more advanced topics like how to translate pointers, how to translate functions or arrays or structs.